everyone. For our next session, we have two very exciting papers that sort of speak to each other. They're both invited talks. They are papers that have been published elsewhere. And what we're going to do is each one of them is going to speak for about 25 minutes. After the first one, they'll take one or two quick clarification questions. If you have a short question, feel free to ask it at that time. And then at the end, we'll take whatever remains of the hour and have a sort of a discussion about how the papers speak to each other, and we'll take a full set of questions on both. Without further ado, I'm going to turn it over to Adam and James, who will be speaking on bias in word embeddings, our first of two papers on this topic, both relating to natural language processing. Thank you.
Great. Well, first of all, thank you so much for inviting us. James and I are going to present this paper. It's an upcoming paper at NIPS, which is a machine learning conference, and it's joint work with Tolga Balikbasi, Kai-Wei Cheng, and Venkatesh Saligrama. And this is a paper about, not about prediction and making fair predictions, but about the representation of the data, the underlying way we represent the data, which lets us kind of peer inside a machine learning algorithm and see how it's working. Could help us debug things when it's not working, but it's also understandable to humans, I hope, in some ways. So it's an interesting opportunity to make algorithms more fair, I think. So what is a word embedding? Let me start with that. So currently, the way we train in word embedding is we take a bunch of text, or this is not us, this is what other people have done. We just take their embeddings. They take 100 billion words of Google News, let's say. They put it into some algorithm, and it pops out with a word embedding, which is, you can think of it like a giant matrix. There's a row for each word. They have hundreds of millions of words. And then for each word, they have, let's say, 300 numbers. And you can imagine that for a computer to represent a word as numbers is actually much better, much easier for it to understand than as a bunch of letters. It doesn't know what the letters mean, but the numbers it can deal with. Okay, and then so you have for each word somehow 300 numbers, and I'm not going to talk much about how they get those numbers. And then computer scientists get excited. They know it's working because they see things like there are these parallelograms which help it understand analogies. So you ask the computer, woman is to man as queen is to, and then it looks for the nearest word in the missing spot in the parallelogram. It pops out with king, and you say, aha, so this thing is sort of understanding language. This is great. And so basically, you should think of this word embedding like a dictionary. It's a dictionary that helps the computer understand language, English, let's say. And there's, already thousands and thousands of papers, even about just one of these embeddings called Word2Vec that we'll talk here. So people are using these all over the place. So just to illustrate, the concern, though, that you have here is that these dictionaries are biased. I mean, how upset would you be if you looked in the dictionary and it said a nurse is a woman, right? That would be very upsetting. The dictionary is supposed to be for our children or people who don't speak the language or people who understand the language but don't know a word to look up and understand things, and it would be very upsetting if it said a nurse was a woman or a computer programmer is a man. We would all be very upset. And I gave this talk a while ago and actually made a joke, which sadly is not a joke anymore. No, it's really true. I mean, when I gave it before, I sort of felt like, well, we all know, we all agree that this would be terrible, but now I don't even feel confident to say that everyone agrees that this is terrible. It's not, sadly, it's not really clear that everyone would agree, but among those of us who want to design algorithms that are not biased, we would all agree, I hope, that we don't want our algorithms to be looking in dictionaries that are so biased. But just to show you, I mean, people, there's, here's 16,000 views. People are asking, where can I find these word embeddings because they're so useful in applications, okay? And just as an example, how would you use a word embedding in an application? If you were building a search engine, or even, let's say, a search engine for resumes, and you wanted to search a pile of resumes for a programmer who lives in Cambridge or whatever, you might, the algorithm, could just look for resumes that have the word programmer, but now the word embedding, since it knows which words are close to one another, there's sort of a distance between these numbers, it can say, oh, programmer is close to JavaScript and Python and computer science and engineer, so even if the resume doesn't have the word programmer in it exactly, it might be able to bubble up anyway. So that's great. That's why these word embeddings can make things work better. But then you see, this is what we noticed, if you look in this embedding, you'll see that the word programmer is also closer to the name John than Mary, which is a problem. And it's closer to he than she, and it's closer to football than softball. So, and that's because we know that these things are trained on natural language text as it appears in the wild, and like that's where the statistics are coming from, the biases that we have in our world. But that could pose a problem if two people are applying for a job, and already there's a lot more male programmers than female programmers, and now you're going to push down the female programmer's resume, even if it's identical to the male resume in every other way, except for the person's name or sex. Okay, so that's a problem, and people, I don't know, we want to make sure, first of all, that people are aware that that's a problem. There's already multiple papers just on this topic of using word embeddings to rank resumes or to do job matching. So, and they're used all over the place. This is just one example. You can kind of imagine any application that wants to use, to understand text, loves to use these dictionaries, these word embeddings, okay? So, so we need to take that into account, and what can we do about it? And we're not going to give a complete solution, but we'll talk about, in this talk, gender bias, specifically male-female gender bias. But of course, there's other kinds of biases that we need to address as well. But this is just giving us a first step in thinking about this kind of question and how it could be addressed. So what I have here is I'm showing you some words from the word embedding plotted on two axes. The first axis, so these are kind of like columns in the matrix that I talked about, but they're not actually columns, they're directions in the embedding, so it's some combination of columns. But what we look for is, we have 300 dimensions in the embedding, but I can only show you 2 of them. So we look for directions that capture meaningful things. So if you just take the word he on one side and the word she on the other side and see see how the words fall out in terms of what's closer to he or she, you do see that there's that the word embedding does correlate with what humans might think of as biases, sadly. But you see a lot of things here that, genius is much on the more male side, and nurses are on the female side. So you see the embedding has captured the biases of people. And we did some experiments to show that they're consistent with human biases. James will talk about that. Also interesting is that there's another direction. There's a line here I've drawn that none of this is perfect, but there's a lot of accuracy here, and we measure the accuracy. There's a line that separates in a different direction that we found in the embedding, a line that separates the words which are, you might say, definitionally male or female, that gender specific, that should be, a brother versus a sister, grandmother, things like that, which have a gender inherently by definition. If you looked in the dictionary, you would want to see that. And the other words which hopefully, shouldn't have a gender, okay? So the word embedding not only knows male and female, it also sort of knows what's sexist. It's a sexist embedding, but it knows, because it's been trained, somehow that sexism got captured in the embedding as well, which means that we can maybe use the embedding to remove this sexism. By the way, this is not only an algorithms problem. It would also be okay if somebody sat down and made their own embedding and you can move these words around, and you could have a dictionary maker get together with a linguist and a mathematician, and they could create an embedding, and it's like a dictionary, right? So, but typically we're computer scientists, so we try to create these things algorithmically. So we're happy that we can see this division in the data, and we don't have to make a huge list of words ourselves. So you see the sexist part here, and then what we can do is we can move the words around. Oops, sorry, wrong. And we can move the words around, and we can create a different embedding, which hopefully is not as biased, okay? And you could even make the claim that it's easier to debias an embedding, for an algorithm to debias an embedding, than it would be to debias a person. So if you went to the HR manager at some company and you said, hey, please ignore gender when you're hiring, they might, try to do that with their best of intentions, but that's really hard for them. And then it'd be hard to go back and look at their decisions. Whereas an algorithm, you can move these words around. You can, if it's not working, debug it, adjust it, see the decisions it's making. You can, after the fact, go back and audit them. So you do have a lot of accountability and transparency in these embeddings. Okay. So another thing, as I mentioned, these analogies give people a lot of confidence or an insight also into the word embeddings, and it works really well with a lot of things like man is to king, woman is to queen, Paris is to France, Tokyo is to Japan, and there's some kind of geometry here that's explaining all these analogies. So what we did is we started asking the computer to generate a bunch of he-she analogies, and it came out with he is to blue as she is to pink, and it came out with he is to brother as she is to, which is good, and he is to doctor as she is to, he is to sausage as she is to, it came out with buns. The computer, this is trained on the Google News. I don't know why that came out, but he is to realist as she is to feminist. She is to pregnancy as he is to, kidney stone. So yeah, the computer's not that bad. And then as in the title, he is computer programmer, she is the homemaker. So you thought, oh my God, that's what's in this dictionary, which is used in thousands and thousands of papers. And also I've talked to people who are using this in systems. So first of all, people need to be aware that this embedding has a lot of bias in it, and they need to think twice about just using it wholesale in an application. And now I'll pass it over to James.
Okay, thanks, Adam. So I'll explain in a little bit more detail of how do we actually quantify and characterize what are the biases in the embeddings. Right? It's going to be quite interesting because they show up as interesting geometries in these word vectors. And then I'll describe how we actually leverage the geometries to automatically debias the embedding. So we developed 3 metrics, complementary metrics, to quantify how much gender stereotypes is in an embedding. So the first metric is basically we're going to project occupational words that should be neutral onto the he-she axis. Right? So to explain what this means, right? So remember that what the embedding does is that it takes every word and it assigns a vector corresponding to that word. So in particular, I can take the word corresponds to he and the word corresponds to she, and I can look at the line along that word, and that's sort of supposed to capture what the embedding thinks as being the differences in the genders. And then I'm going to project about 300 occupations that are supposed to be gender neutral onto that line between he and she. Right? So each word here actually corresponds to one of the embedding vectors. I'm just doing the projections. And when you do this projection, something quite striking comes out. Right? So the occupations that are closest to she ends up being things like the homemaker, nurse, receptionist. Right? So these are the words, the occupations that the embedding thinks is closely related to the word she. Right? Because remember, the distance in the embedding corresponds to semantic similarities. And on the other extreme, so if we look at words that are occupations that are closest to he, then I have these different sets of occupations. All right, so that's quite striking. So what we decided to do is to make this really systematic. Right? So for each of the occupations, in parallel, we're going to go on Amazon Mechanical Turk and we ask crowd workers to rate each of the occupations as to how much male or female stereotype is typically associated with that occupation. Right, so we do that for each of the occupations, and then we can compute sort of a correlation between its values on the projection of the he-she axis and what humans think is being the stereotypes of these occupations. And there ends up being a very strong correlation. Right, so this shows that the geometry of these embeddings, at least for occupations, seems to really capture human notions of stereotypes, gender stereotypes. So there are thousands of papers, as Adam said, that looks at different embeddings and different methods. Right? So we looked at some, and we're interested in saying something that's sort of consistent across different embedding methods, and ends up that this gender stereotype is really consistent across different embeddings trained on different documents. So here I'm showing you sort of 2 of the most commonly used embeddings. So there's a word-to-vec embedding that's trained on a large corpus of Google News documents. That's the x-axis. And the y-axis corresponds to a different algorithm, GLOVE, that's trained on a very different corpus. Right, so each dot here corresponds to one of the occupations. And the axis corresponds to, again, the projection onto the he-she axis in each of the embeddings. So you can see that there's actually a very consistent stereotype agreement across the different embeddings, even though they're trained on different corpus using different algorithms. So the occupation projection is quite informative and it's easily interpretable, but it's restricted to a particular set of words. Right, so we want to do something that's much more general that uses the entire embedding set. So the idea that we have for the second metric is to automatically generate analogies from the embedding. So here's how it works. Right, so we look for analogies of the form of he to x is as she to y. Right, so what makes a good analogy? As Adam's saying, an analogy usually corresponds to these parallelograms in the embedding space. Right, so what it means is that he to brother is as she to sister is a good embedding by the it's a good analogy according to the embedding because the angle between these two vectors is very small. Right, so we can formalize this as the optimization problem and just ask the embedding to automatically generate what it thinks are good analogies for this he to x is she to y. So here are the different analogies it generated as being good analogies. And again, we go back to the crowd to ask, okay, so for each of the analogies, how much does it exhibit gender stereotypes according to the crowd workers? And again, we found that about 1 in 5 of the generated analogies were rated as strongly gender stereotypic according by a majority of the crowd workers. So there's a lot of stereotypes systematically encompassed in these embeddings. So the third metric we developed is sort of more subtle kinds of bias. So the idea here is that even if I look at words that should be gender neutral, right, their relative distances and their geometries could be affected by gender stereotypes. So here's an example of this. Right, so instead of projecting onto the he-she axis, let's project the occupations onto the softball football axes. Right, softball and football really, in principle, should be gender neutral. People of all genders play these sports. But you find here is that occupation like receptionist is actually very close to softball. It's not because that receptionist is, the occupation itself is very close related to softball. Right? So that happens because there's a strong female component according to the embedding that's behind both receptionist and softball. Right? And similarly, with maestro and football, I don't think they're actually occupationally related. It's just that there's a strong male component to it. Right, so there's this subtle kinds of indirect or secondary bias that shows up in the embedding. Okay, so how do we, now that we can quantify the bias in embedding, how do we go about trying to de-bias it? The idea here is that there's actually a lot of interesting geometry that we're seeing that's in the embedding, and we want to leverage that geometry. So one kind of geometry that is quite useful is that, so we're seeing, one of the nice properties of the embedding of these word embeddings is that quite complex higher order semantic relationships are actually captured by relatively simple linear operations. Right, so this led us to conjecture that maybe we can find a linear operation or maybe a linear subspace that captures a lot of these gender components and gender stereotypes. So the way that we've ended up doing this is to start with a set pairs of words, right, that really captures gender opposites. So here are some of the pairs of words. Right, so if I take a particular pair, like man and woman, then that definitely captures quite a strong gender component, but maybe there are also other aspects to men and women that's not independent of gender. Right, but the hope is that if I take a lot of these different pairs of words, then maybe the shared directions or shared subspace that's common across different pairs tends to capture more of the true gender component. Right, so operationally, that means basically by looking at the principal components across these different pairs of words to see what are the subspaces. And when we did this exercise, it's very striking that there's one very clear direction, one-dimensional subspace that seems to really capture a lot of the differences between these pairs. Right, so we use that as our gender subspace, the first principal component. Okay, so then the strategy that once we have identified this gender subspace is very intuitive. So I'm going to give sort of the simple version of our algorithm. So the idea here is that let's first identify words that we think should be gender neutral and words that should be gender definitional. right? And then on the words that we believe should be gender neutral, we should project away its contribution from this gender subspace. We should remove that altogether. And then the last step is to sort of normalize these vectors so that they're useful for the embedding and, as embeddings. Okay, so how do we find words or that are gender specific? Right, so this is quite a subtle question, and there are different versions of this, depends on the application. But as a first approximation, we took a rather strict approach to doing this. Right, so we say that we're going to identify the words that are, by definition, associated with one of the genders. Right, so there ends up being a relatively small number of those words. And we're just simply going to say that all the other words, the rest of the words, should be gender neutral. Right, so this is quite a conservative definition that we want to use here. So we can identify the gender definitional words either by hand, since there's only a small number of them. And it actually turns out that we actually can develop a sort of SVM, a linear SVM that identifies those words. Right? So it turns out that they actually live in a different part of the embedding space from the other words. All right, so that definition, as Adam said, is already encompassed in the embedding itself. Okay, so now that we identify which words are gender neutral and which words are gender specific, what we're going to do is that take all the words that are gender neutral, and it's going to remove their gender contribution, i.e. project away the gender subspace. Right? So there are going to be claps on the gender subspace. They have no longer any gender contributions, but they still have these 299 other dimensions to explain all the other interesting differences between these words. Right, so these are 300-dimensional embeddings. And we're not going to change the words that should be gender definitional. Right, so there, okay, so there's sort of the intuition behind the algorithm, and then there's sort of a slightly more sophisticated version of the algorithm that does this in a more subtle way. Right, so don't worry about the particular equation here. I mean, the main idea of the advanced algorithm for debiasing is to simply balance these two objectives. Right, so the one objective is that for the words that are gender neutral, we want to reduce its contribution from the gender subspace. At the same time, we don't want to move and change the words too much. Right, we want to preserve its original geometry as much as possible because there are still interesting utilities from that geometry. So operationally, that turns out to be this particular semi-definite program, and we have techniques for solving this quickly. Okay, so here are the results from the debiasing. Right, so the first plot here corresponds to the number of stereotype analogies that's generated by the embedding. Right, so the x-axis corresponds to just ask the embedding to generate more and more analogies. And the y-axis, we go to the crowd and ask, okay, so which of these analogies shows strong gender stereotype? So the blue curve corresponds to what was happening in the original embedding. Right, so as you generate more analogies, sort of a large fraction of these shows up to be gender stereotypic. And the green curve corresponds to what happens after the embedding. Right, so as you see that we effectively really reduce the number of analogies that are judged as to be stereotypic by the crowd workers. At the same time, we also want to track that the embedding is still useful, right? It's still generating useful analogies or appropriate analogies. And you can see here is that basically our algorithm does not, even after doing the debiasing, we're still generating roughly the same number of useful, appropriate analogies as was before. And we had a lot of other metrics to show that, based on word similarities, et cetera, to show that this debiasing operation that we have, by projecting with the gender subspace, really does not affect the overall utilities of the word embeddings. You can still use them for a lot of the tasks you want to do before in NLP, but it is very effective in removing the gender stereotypes. And it's also effective actually in reducing this more subtle indirect bias. Right, so as we saw before that, okay, so here in the original embedding, we see the strong indirect bias. And in the debiased embedding, in this example, so now we no longer have this association between receptionist and softball. Instead, you have sort of major leaguer and softball, which is a much more reasonable, appropriate association. Right, so this debiasing operation also is effective in reducing secondary indirect bias. I just want to quickly mention that while here we focused on gender stereotypes, there are lots of other very complex stereotypes, ethnic, cultural, religious stereotypes that are all shows up as as different geometries in the embedding. And I think there's a lot of interesting work to be done in trying to characterize these other stereotypes. And here I'm just showing you sort of a few examples that we found, in particular for racial stereotypes, how that shows up in these embeddings. Okay, so going back to Adam's slide, right? So what we're really trying to do here is that these embeddings are really used as dictionaries for algorithms and for machine learning programs, right? And what we're trying to do here is to come up with a technique that produces, as much as possible, a debiased or unbiased dictionary, so that the program doesn't sort of propagate these stereotypes downward. It's still quite an early stage work, and there's a lot of interesting points of discussion here. So one question is, right, as we're thinking about this, we should think about like, who is really responsible? Is it for these different biases? Now, is it the data itself, the original corpus, the training set? Is it the particular embedding learning algorithms, or is it actually the downstream machine learning application users? Right, so our feeling on this is that, so there are a lot of subtle biases that's in the original embedding corpus. Right, so if you just take New York Times or take Wikipedia, so there are subtle biases as a form that maybe he tends to co-occur more frequently with doctor, and she tends to co-occur more frequently with nurse. What the embedding does is that it takes these subtle biases that's in millions, hundreds of millions of documents, and it really crystallizes them by compressing everything to these 300-dimensional spaces, right? And by doing this compression, so it really crystallizes like what are the biases in its original corpuses, right? So there's a lot of responsibility to be shared across all of these different actors. The second point here is that we're trying to argue that these embedding algorithms, because they're so effective in capturing these biases, that actually gives us a way to automatically debias these embeddings using its own geometry. Right, so here the geometries we see are of the form that maybe there are linear structures, linear subspaces that captures gender stereotypes, and also captures what it means to be definitional versus neutral words. Right. And the third point really goes back to the heart of this workshop, which is that these embeddings has this funny feature that they are in some sense very transparent and quite interpretable, right? More interpretable than a lot of other machine learning algorithms, which is one reason why people like them. And for this particular setting of stereotypes, the interpretation has this double-edged sword in that it allows us to also quickly identify and visualize what are the gender stereotypes that's in these embeddings. And this makes it actually easier to debug these embeddings compared to a lot of other machine learning algorithms. And then this leads to the last point of, so how should we actually think of this work going forward if you actually use it for applications? So I think what we try to argue here is that whenever you're using these embeddings, as one of the inputs into your machine learning applications, you should, in parallel, take this input or debiased embeddings, right? So, and it would be a good sanity check to see, does that actually, if you run these on the original embeddings, on the debiased embeddings, if you run your algorithm downstream application forward, does it actually make significant changes in the outcomes, in the results? Like if the outcomes, if the resume rankings or the search rankings are very different, that should be a warning flag that maybe there's something going on, and maybe you should go back to your original embeddings to try to debug it. Right? So we're not saying that you have to use the debiased embeddings, but we think that it is useful as a sanity check to run it in parallel to see how much difference does it make in your downstream machine learning applications. Great, thanks.
If people want to ask a short clarifying question, now would be a good time.
Have you talked, very nice work, but I was wondering, have you talked to any trans person during this research? And there is a deeper issue here, right? I mean, you are starting from some
Yeah, so I think that's a great question. I mean, so here.
So if people ask questions, please, for the live stream.
Yeah, okay, actually, you can just repeat my
Repeat the
question.
question.
Okay, so the question is that, so here we talk about 30 years of male-female biases. Have we looked into sort of, the transgender issues and more complex situations? So I think that's a good question. So what we're trying to do here is to maybe just give sort of a first pass look at this issue. It's definitely a really complex problem. And as I mentioned, so there are lots of ongoing work to look into the more these more fine-grained and more subtle types of biases, including the transgender and also racial biases. But for this particular work, we're just only looking at this sort of fairly binary bias. But it is a good point.
Hi, my name is Lucia Sommer, and I come from a criminal law background, and I was wondering if like the basic notion that of your research could also be applied to debiasing algorithms in a criminal law context. For example, the recidivism prediction that was mentioned in the opening panel, the ethnicity bias that is in the recidivism predictions. Could it also be used for that, to debias that?
Good question. So a difference between what we talked about in a lot of other work is that we're talking about debiasing at the word level. We're debiasing this sort of dictionary representation, which could be used in one of those applications. Usually people talk about debiasing the outcomes, the predictions themselves, and looking end to end. And we're talking about this middle ground where we actually try to debias the dictionary itself.
Yeah, so it is a good point that if there are algorithms that's doing maybe crime prediction or recidivism prediction that uses input these word features. I don't know if there are algorithms, but let's say if there are these algorithms, then I think it is important to see what would happen to those predictions if you use the debiased embedding versus the original embedding.
I know there are a ton of questions in the audience, but in the interest of keeping us on schedule, I'm going to hand things over to Arvind Narayanan, who's also going to present about bias in word embeddings. And Arvind, take it away.
Thank you, Josh. Here's why I'm super excited to be here today. Often in science, there are simultaneous discoveries, and then people fight about who gets credit. But sometimes, more interestingly, two groups of people look at the same data and make the same or similar observations. But come to very different conclusions about what this means and how we should respond to it. So I think we have a case of that here today, and that's actually a really good situation to be in. Because in the process of figuring out how to reconcile these divergent views, you end up discovering something new that neither group individually discovered. And so that's my hope about what's going to happen today and in the ongoing conversations that I think this community is going to have about these findings that I'm going to share with you in relation to the findings that you've just heard about. I want to say quickly that Eileen is here in the first row if you want to wave, and she's going to be up here during the Q&A as well. She's the lead author. You're welcome to address any questions to her as well. So we think debiasing that they've presented is a very cool algorithm, and it's going to be very important and it's very interesting. But we think it's not really going to solve the problem. And the difference in our perspectives comes from what we're arguing is that what you're seeing here is not specific biases like gender biases or racial biases, although that is certainly true. But as I'm going to show you, machine learning imbibing essentially the entire spectrum of human biases. And I'm going to show you a rigorous way of establishing that. And also, I'm going to argue that there is no clear dividing line between what we consider meaning in the data and what we consider bias, and in particular, unacceptable bias that we want to get rid of. Further, as Adam and James mentioned, these word embeddings are in dozens of different systems. And I want to argue that it really depends on the application what we want to do about these biases. What constitutes a terrible bias, a prejudice in one application might actually end up being exactly the meaning that we want to get out of the data in another application. That sounds counterintuitive, but I'm going to give you an example of that. So based on all of these, I'm going to argue that we should think of these biases not as a bug in the system, which is the metaphor that you guys used, and it's an interesting metaphor, but I'm going to argue that we should think of these as a feature of these models. And at first sight, that might sound horrifying given some of the examples that we saw in the previous talk, but I will explain why we have that point of view, and that will lead to our suggestion for how to deal with these is not that we should debias, at least not in all cases. However, we have to start trying to build explicit components of AI systems that understand the concept of bias, of prejudice, and have ways of mitigating it instead of trying to eliminate it from the system. Okay, that's a lot of abstract stuff, but now let's dive into the details, and let me explain why we came to this point of view based on somewhat similar findings from the data. Is it possible for me to grab this mic, by the way? That would be super useful. You want to hold it? Yeah. So here are the research questions that we were interested in. Thank you, Solon. Why are word embeddings biased, and how biased are they? And those two first questions really occupied most of our attention. How should we address this bias as sort of a consequence of our research? But we really wanted to more rigorously understand bias and quantify it and so on. And I want to point out that the broader concerns that we're going to raise here are not specific to word embeddings. For us, word embeddings are a tool to understand this concept. They're a messenger, they're a symptom of the problem. They're not the problem itself. So we think that debiasing word embeddings is misplacing the focus a little bit of where our intervention should be. I'm going to try to convince you that there's something deeper, more fundamental going on here, and something fundamental to human language and to our biases as well, and how that's being reflected in machine learning systems. In other words, the hypothesis that we're proposing is that essentially all human biases are reflected in semantics. And that's not an obvious point, that these biases should even be reflected in the semantics of language, much less in purely the statistical parts of language. Right? And that's not a point even about machine learning, it's a point about humans and culture and language and so on. And we're going to see how our data presents evidence for that. And if that's the case, then that becomes easy to believe that inevitably these are going to be imbibed by machine learning systems, whether it's word embeddings or any other kind of model of language that you're working with. So how can we do this? How can we make this connection between human culture and language and what's going on in machine learning systems? And the fundamental way that we do it is by using what is called the implicit association test, which is a well-known test of human bias in psychology and cognitive science, which has been established over the last couple of decades. And it's a way to understand and even quantify biases and prejudices that people have. And here's how it works. The concept is really simple. Imagine a test subject here who we hypothesize, has the stereotype that boys are good at math and girls are good at reading. So here's how the test works. The subject is going to get a sequence of words, one by one, projected on the screen. On the right, you see the sequence of words. And the subject needs to press the left button if that's either a math word or a boy name. And she'll press the right button if it's either a reading word or a girl name. And the idea here is that if this test subject does indeed have the stereotype in question subconsciously, they may not even know about it, then it will be the case that this task, which is stereotype congruent, which conforms to the stereotype, is going to be easier than the opposite pairing, where you pair the boy names with reading words and the girl names with math words. Right. And so if you do this test enough number of times, enough trials, what you're going to find is that the reaction times of pushing the left or the right button is going to vary. And these differential reaction times, it turns out, they're not going to be dramatically different, but you're going to get two distributions, and those distributions are going to have means that are separated. That differential reaction time is a measure of the bias in humans. And this is the implicit association test. There are hundreds of papers on it. It's really well established in psychology and cognitive science, and the implicit association test was the starting point for us. That's sort of the definition of what we mean by bias in humans, and we want to take that and try to see how well that applies to word embeddings as well. So the main contribution in our paper is we came up with what we're calling the word embedding association test. We want to come up with a test that mimics the setup as closely as possible. We want to apply it to word embeddings. So that's what we managed to do. The statistics are in the paper. I'm not going to go into them here. But roughly, the intuition is that these word vectors, they're vectors in high dimensions, so you can compute the angles between them. You can compute the cosine similarity scores. And it turns out that those cosine similarity scores, intuitively, they measure the similarity between pairs of words. And you can use that more or less in place of these reaction times that are measured by the implicit association test. I should mention one caveat here. This is what makes the word embedding association test a little bit tricky and not totally straightforward. which is that for us, there is no notion of individual test subjects. What we're working with is these corpora of text found online, and these corpora, you can think of them as being the aggregate output of millions of individuals. And so the tests that we come up with make statements about language corpora on an aggregate basis and not at the level of individual humans. That requires redoing the statistics a little bit, but we can do that, and we've managed to do that. There's also one quick thing I should point out about the implicit association test and why we think that's really powerful for studying these biases in machine learning systems, is that as the term implicit association implies, the test is able to elicit biases and prejudices and stereotypes that the subjects may not even be aware of by themselves. And I know this from personal experience from the first time I took the test online in 2004, and if you take the test, many of you might find that as well. So that's a really cool, powerful concept. So we have hundreds of studies in psychology that have documented these in humans at an individual level and an aggregate level. They've quantified it, and now we can have an analog of that test for machine learning, and we can see how word embeddings perform when they're put to the test. So let me show you the details of that. Here are the data and the algorithms that we use. Now, we wanted to make sure that we were basically using pre-trained embeddings. We didn't want to train our own embeddings because, as James pointed out in his slides, people are using these existing embeddings out there that researchers have put out in a variety of different systems, and we wanted to mimic that as closely as possible. So we used the pre-trained word embedding, by the GloVe algorithm, which is the Stanford project, which is a state-of-the-art research project. It's pre-trained on the Common Crawl corpus, which is a huge corpus. We also repeated our tests with this other corpus, Word2Vec, trained on Google News. Very similar results, but the numbers that I'm going to be reporting here and in our paper are based on GloVe, trained on Common Crawl. Okay, without further ado, here are our findings. There's just one quick sanity check that I want to do here before going to our findings, which is a sanity check that's used in the implicit association test itself. In addition to characterizing biases and prejudices, the IAT is also used to characterize just universal associations that everybody has in our heads. Associations between flowers in pleasant terms and insects in unpleasant terms. So that's something we can look at the implicit association test results and try to reproduce in our algorithms and in our models. So you have a basket of flower words, you have a basket of insect words, and then you have baskets of words for pleasantness and unpleasantness. So in this and each of the further studies that I'm going to be showing you, we try to reproduce both the, reproduce the same set of words that were used in the original implicit association tests, and we're going to look at the effect size of the bias that measures how well these two distributions are separated. Right? How much closer are flower terms to pleasant than unpleasant terms compared to insects? So this is a universal association. Everybody has this. So in the original finding, you have an effect size of 1.35, which is considered a really huge association in psychology. And that's fairly intuitively obvious. Everybody considers flowers more pleasant than insects. And similarly, we reproduce a really huge association with word embeddings as well. So far, so good. Sanity check. And this is, we have statistical confidence. P-value is less than 10 to the minus 7. Now we get to the interesting stuff. We started looking for IAT results on racial bias, for example. And so we were able to find studies with baskets of European American terms and African American terms, and the same basket of words for pleasantness and unpleasantness. What we found was in the original study, again, a pretty big effect size. This is considered huge in psychology. And with the word embedding as well, we were able to reproduce that, actually an even larger effect size here. A quick caveat that I want to point out is that it's not meaningful to compare the p-values between the two because the subjects, so to speak, in the original IAT are the participants, whereas in our test, they're not exactly the same statistical test. The notion of subjects is replaced by the notion of names that we have here. And so the p-values just have different meanings, but I think it is meaningful to compare the effect size. And the fact that these effect sizes are so huge is really telling us something, that these biases are really captured in the statistical properties of language. And I think that is somewhat surprising quantitatively how big these effects are and how well they're reproduced in these word embeddings. Next, we looked at stereotype biases in terms of gender. So we looked at female names and male names, compared that to family words and career words. Again, reproducing what was done in the original IAT. Female names are stereotypically associated with family terms, both by human subjects as well as by these word embeddings. Again, reproducing pretty big effect sizes here. Another type of gender bias, we're looking at science words and art words and comparing that to these two baskets of words here, again, finding similar things. So I won't keep boring you with these numbers. Over and over again, we're finding the same things. We did even more IATs for age, religion, physical versus mental illness, and so on. Essentially, every IAT that we could find that used names in the original test as opposed to images and whatnot, which we can't quite reproduce, we were able to reproduce their findings, both qualitatively and in terms of the magnitude of the effect size. So what I want to claim here, the fact that this is happening across the board with all of the biases that we have tested, is pointing to something deeper. It's pointing to the following account of bias in AI systems. What it's telling us is that human bias, at least as documented by the IAT, is captured in the semantics of language, and that is further propagated to the distributional meaning of words, and that is getting picked up by these machine learning models. Right, so I think our results taken together provide support for each of these three implications. And this first arrow in particular, it's not even a statement about machine learning, it's a statement about humans and how deeply our biases are embedded in language, and we think that even has implications for human bias and prejudice. There's a part about that in the paper. I won't go into too much detail on that. But it suggests that we're dealing with a deeper problem here. It's not going to be something that we're going to have really an algorithmic fix for. Yeah, I'll skip what this is about. Okay, here's the part of our paper where we start to say more controversial things, at least contrasting to the talk that you just heard. Now we can ask the question, how should we address bias in AI systems? And you can come up with several potential ways we can think of addressing AI bias. Just modify the training process, whether that's the training algorithm or just the culture of the tech industry, whatnot. There's various things that have been proposed. All of those are certainly useful. This middle bullet is what we just heard, the debiasing technique. Or this is something that's often something that you hear from Silicon Valley CEOs and engineers when they're asked about these biases. Oh, it's just a problem with the training data. The biases in the data set, humans are biased, they're gender stereotyped, and that bias is reflected in language, and we're picking it up. When humans are in this perfect unbiased state sometime in the future, then our models will also no longer be biased. It's not our problem. Right back to you. It's your problem. Right? And I'm not making this up. There are quotes about this. This is when what machines are picking up on, this claim goes, are not facts about the world. They are facts about the data set. The real world is unbiased, but humans, in the way we speak, are racially and in terms of gender, we're biased. So goes this claim. Let me give you evidence that this is an oversimplification, that even completely factual real-world information about our world today is going to be expressed as biases and prejudices in these machine learning models. And the way I'm going to show this, I'm going to compare this to a slide that you saw in the previous talk, which said, if we look at crowd workers on Mechanical Turk, elicit stereotypes from them, and look at what the word embeddings are doing, there's a correlation of 0.5. Let me put a twist on that. What we decided to do is we looked at not how biases are expressed in Mechanical Turk workers, but just purely factual information about the world. We looked at government statistics of 50 different occupations and what percentage of workers in each of those occupations are women. This is released by the Bureau of Labor Statistics. We looked at that data, and we decided to compare that to how gendered does the word embedding think each of those occupations is. And we put that on a scatter plot. You saw a correlation of 0.5 earlier. Look at this correlation over here. We were astounded. We were expecting a correlation, but not this much. This is 0.9. So let me explain again what you're seeing. On the x-axis is purely factual data about the real world, the percentage of workers in each occupation, doctors, nurses, programmers, so on, who are women. And the y-axis is how close the word embedding things is each of those occupation word vectors to feminine word vectors as opposed to masculine word vectors, right? So forget about the ethical implications for a second. Just from a technical perspective, this is so cool that this is government data. This is from a 1990 data set. And with a correlation of 0.9, the word embedding is able to infer that purely from the distributional statistics of language from uncontrolled text found on the web. I mean, there are so many reasons why you would expect a worse correlation. This is text found all over the web from all countries, whereas the x-axis is only US data. So that's going to decrease your correlation. In spite of all that, you're getting a correlation of 0.9. This is crazy just from a technical perspective. But But from an ethical perspective, this becomes problematic because now you can see very clearly that whether we consider this to be bias or meaning purely depends on how we want to use these models in our applications. If your application, for example, were to look at historical job ads and characterize whether more men or women worked in those occupations, this is exactly what you want. It would be a shame to throw this away. On the other hand, if your application were to look at resumes and make decisions about the future, of course, this would be a terrible thing to have in your program doing. But at a fundamental level, this is our history and this is our reality today, and I don't think we should edit it out of our machine learning models. It does reflect something that is there in our world, and our response should be instead to find ways, and it's not obvious how to do this yet, it requires a new research program, to find ways to teach our AI systems, our machine learning systems, what this means, what types of biases are acceptable and unacceptable, and to have explicit ways to mitigate this and compensate for it in specific applications. Just one other thing super quickly, to emphasize that that's not a fluke. You can find these associations with all kinds of other things. Here's another one. This is names that are given to both boys and girls. So on the x-axis you have, again from statistics, percentage of people with the name currently in the US who are women. And again, it picks that up pretty well just from the distributional properties of language with a correlation of 0.84. So to reiterate why we think this is a really tricky problem and something fundamental that we're not going to easily edit away is there are several types of things that we're calling bias here. One is just universal, flowers versus insects, totally unproblematic. Another middle category, clearly problematic, such as black versus white names. And a third category is things that are patterns in the real world can definitely be very problematic, but also can be really useful meaning in the data. So you have a confused robot here which has no way of distinguishing between all of these three categories. In particular, what we term to be prejudice or unacceptable bias is going to be a cultural notion. It's not fundamentally an algorithmic notion, and it's going to be evolving over time. Different cultures have different versions of that. And the same phenomenon in the data, depending on your application, can be acceptable or unacceptable. And finally, just factual associations in the data could be manifested as bias or prejudice depending on how you use it in your application. So that's why we think this is a really tricky problem. So to address the debiasing technique more specifically, again, I think it's a really cool technique that you guys found this direction in the data set that actually captures the notion of sexism. I think that is a very valuable tool we should have in our set of tools that we use to think about this problem. However, I think there are important limitations. At a high level, what debiasing is doing is it's altering the AI's model of language, its perception of the world. Right? Because that's ultimately what word vectors are. It is a dictionary, that's one good way to think about it. But it's also a perception of the world, that is also another way to think about it. So if you're debiasing a word embedding, you're affecting something that's used in such a variety of applications in very different ways. And the technique that we heard about earlier relies on this particular geometric interpretation, and it's not clear that's going to generalize to all kinds of biases that we're seeing in the data based on the implicit association test. So what we're proposing, we don't have a concrete way to do this. I should say that up front. This requires a new research program. It's not a very comforting answer. It's not something that's going to happen tomorrow. But I will show you on the next slide something that could happen at a more immediate time frame. But in the long run, we're saying that we need to think about designing these AI systems in a way that we alter the action of the AI, not the AI's perception of the world. That's the key distinction we're making. And the good news about this is this is actually very similar to what, again, the psychology literature tells us humans ourselves are very capable of doing. We know from the IAT studies that a lot of the time, people don't necessarily act on their implicit associations, even strong implicit biases that they have. And maybe something like that should be applicable to AI systems as well. And so this idea of a separate component that's capable of explicit instruction, especially in a non-statistical sense, using symbolic reasoning, is an idea that's totally gone out of favor in AI, right? And so maybe this is one reason to consider reviving those lines of research. It's a controversial point, but it's something that I want to propose to you. And I just want to give you a quick example of how, of a particular application, how these biases manifest, and also how we can think of tailoring our interventions to the specific application. You can try this yourself. This is Google Translate. What you can do is you can pick a language where the pronouns are not gender specific. And this is Turkish. We picked Turkish because Eileen, our first author, is a native speaker of Turkish. And so you can put in Ober Doktor, for example, and O can be either he or she. And when you try that in Google Translate, it's going to come out gender stereotyped. He is a doctor every time. You try the word nurse, it's going to come out he is a nurse, and then he is a professor, she is a teacher. We tried this with that entire list of 50 occupations. We could almost perfectly predict what Google Translate was going to do based on our word embedding association test of what the embedding model considers the gender stereotype of that word to be. So what do we do? But it's not obvious how to address this problem using debiasing. One thing that might happen if you try to do that is it's always going to come out he. That's, you're replacing one kind of bias with another kind of bias. Perhaps, though, and this is going to be a controversial suggestion, perhaps what should be done in these applications is that you should have a separate component of the system that has the intelligence, whether through machine learning or some type of symbolic instruction, to understand that these words here have come out gender stereotypes, and to force the human into the loop, to ask the human user, hey, look, these are potentially stereotypical, gender stereotype translations of these gender-neutral sentences. You have to pay attention to this and figure out how you want to translate this. So we think a lot of the potential solutions to these problems of bias and prejudice are going to introduce more friction into these systems. They're going to take away from our ability to automate all of these. And that's obviously a limitation, but that's something that we should confront, and maybe that's okay, and maybe that's a good thing to have in our systems. It forces us to think about what these systems are doing when we're using these systems. So to conclude, what we wanted to do is, we wanted to understand the problem deeper, and we wanted to provide an account of how and why bias gets into these AI systems. And we did that by looking at the implicit association test. And we think even though all of our experiments are based on word embeddings, what's ultimately going on here is something more deeper than that, is something that really affects, it's going to affect, all of the sophisticated models of language that we're going to build in the future. And perhaps we have to accept that it's going to be inevitable that these biases are going to creep in, that we're not going to perfectly algorithmically distinguish between what's acceptable to have and what's not acceptable to have. And perhaps we need a new research program that seeks to compensate for these biases, sees them as features of these word embeddings instead of bugs in the word embeddings, and learns to deal with it by compensating for it explicitly instead of eliminating it from the system. Thank you very much.
Thank you, Arvind. I'd like to invite Eileen and also Adam and James back up to the stage for just a couple of minutes. If you have a question, we're going to take a few minutes just to sort of have these papers respond to each other. If I could ask you, if you have a question, to come to the center aisle and use the microphone just so that people on the live stream can also hear. In the interest of time, I'm going to have everyone go through and ask their questions all at once, and then have you guys kind of respond to each other. And since Arvind has just talked, we'll start with Adam and James when we get to that. So if you have a question, please come to the center microphone. I'll start it off by asking Arvind, you are proposing that we have a new research program for how to treat biases in word embeddings as features rather than bugs in the embeddings. And I guess my question is, how would you define success for such a program? How would, you gave some reasons that you thought that the approach of the debiasing algorithm was not correct, and I'm curious if those are general criticisms of any debiasing effort, or if how you would define success for something that actually does compensate differently from the way the debiasing algorithm works. Other questions, Suresh?
So one question I had was, I think the framing here is a little bit, at least from maybe Arvind in your presentation, about this whole idea of compensation or elimination, altering actions on perception, which I quite like. But I think there is given that the goal in many of these systems is to automate as far as possible, and this is naturally in conflict with a more integrated human-in-the-loop process where the machine is in. So I think a question here becomes, you kind of want both, but now you have a pipeline of systems that are now plugging into each other. And either you have humans at every step of the way, which might be a reasonable solution to sort of inspect and decide, or you have to have some way of arguing about the way these systems propagate, pushing an automated set of biases through, and then at various points in time, a human injecting into it. So I guess my question is, do you really how do you see, I mean, I personally think that these are not necessarily in as much in opposition as you think, and so I'd like to know from all of you how you think about how they might interact with each other profitably.
So this question is primarily for Arvind, but I'd love everybody's input on it. So when you talk about blaming the problem where we go blame the training data or whatever, my question with that always is well, does the system in particular make the realities that are reflected in that training data better or worse to the extent that we can agree on what better or worse is? And this seems like a particularly hard case for it because we're dealing with human language, but do you have any thoughts on how the kinds of language-related AI systems we build may exacerbate or possibly mitigate the biases that arise from and or cause the bias that we see in the language itself, as a way that we get this big feedback loop, because our systems are going to have an impact on the people that make decisions and respond to them?
Just sort of squat down too. Hi, sorry. I'm just wondering, Arvind, looking at Turkish as a language as opposed to English, I'm wondering if the results, if it's a less gendered language, I don't know if it is, I know at least the pronouns apparently are, mean that the associations that you find in general are less gendered. And I'm wondering about something like Hebrew, where even all the verbs are gendered, whether there's some ultimate effect in the kinds of associations you'll see, if you've done any of that research or their thoughts on that.
I'll just quickly say one sentence in response to that, and then we'll give it over to you, Adam. Certainly, the big next step, one of the big next steps we want to get to is look at a variety of different languages and models trained in different languages. We haven't gone there yet. I do know that Eileen has done similar tests that she did for Google Translate in a variety of other languages. I don't recall off the top of my head the results of that. I don't know if you want to say something about the test that you did, or.
Oh, so we tried most of the languages that have gender-neutral pronouns, and based on that, the results are very similar to Turkish. But for other languages that have more gender information, for example, Hebrew with gendered verbs, we haven't looked at those, but this is a very good direction to see if it is augmented in such languages.
So let me try to address some of the questions, and also this work, which I think is great, and it's much more thorough in some ways than what we did, which was just look at male-female, and you looked at racial biases and things like that. But I still think, using the dictionary analogy, think of these word embeddings as a dictionary. So what I would take away maybe from your work is that maybe we should have different dictionaries, just like there are legal dictionaries. In a legal dictionary, the word grandfather might refer to grandfather-in-law, whereas in a general dictionary, the first definition of grandfather might be as your father's or parent's father. I still think there's a role, since tons of people in machine learning are using these things and just downloading them wholesale and we can't stop them, there's a role for producing less biased embeddings that have fewer biases and will hopefully improve the downstream performance. Addressing one of the questions was, this won't solve the problem, but it will help. Also comment that Max Larson there is kind of doing something at the merger of these two papers where he's looking at names as a way to try to remove biases, not just male-female, but try to de-bias things, both in terms of names, age. Marilyn is an old name, my mother's name, Marilyn, my daughter's name is Maya. Age, race, all these things. So you can try to get a whole swath of biases at once.
All right, thanks, Arvind, for that for the really interesting talk, and I really like the paper too. So I think our work and Arvind and Eileen's work is actually quite similar in many regards, right? So the things that we agree on is that, first, it's really important to point out that these embeddings have very strong gender stereotypes and other kinds of biases, and we developed complementary ways to do that. And the implicit association test is a really nice way to do that as well. I guess what I would like to say is that, from a engineering perspective, right? So it's really important to point out that there's this problem and then to set forward the agenda for a really interesting research direction. But we also want to have sort of engineering algorithmic solutions, right? So I'm at Stanford. Every week I have like 10 startups that's downloading these word embeddings and using it as the one part of their pipeline, right? Maybe that's the input into their pipeline. They're not thinking very carefully about like, what are the downstream applications of this or downstream implications of this. And they definitely don't have the resources to go in and have human at every loop of this pipeline process. Right, so what we would like to say to them is that, okay, if you're going to use this word embedding as a part of your pipeline, then you should at least try this slightly less biased version of the word embedding and see if your results change. Right, if you're doing recommendation systems or their favorite app for their startup, they should see if the results change. And if the results do make a big difference, depends on which version of the embedding you use, then you should go backward and try to figure out what's causing the problem. Right? Maybe in the specific application that they care about, maybe that's not what they're interested in, but there are applications where you could have really, as we've seen, you could have really detrimental downstream effects. Right? So I think that our two strands of work is actually quite complementary in that, we both agree that there is definitely a need for a research agenda to point out these problems. There are thousands of papers published on word embeddings, and none of them actually say anything about these problems. But we would like to say that, okay, in addition to having just the academic discussion, one thing that's really needed especially for the industry applications, which is going on everywhere now, is to really have engineering solutions to this.
We're talking about engineering solutions, but for example, with the crowdsourcing part, how are you planning to iterate over that each time?
Yes, so that's a good question. So that is actually what we just have to do once for our project, right? So we have released so we had to do that to validate that our debiasing algorithm is effective by some metrics. But once we've done that, then we have released our debiasing algorithm, or actually the debiased embeddings, so that any of these startups, if they're using this, they can use it exactly the same way that are currently using a Word2Vec or GloVe embeddings. They don't have to rerun the algorithm or rerun the human experiments.
And that's only for the gender bias.
That's right. So far it's for the gender bias, and as Adam said, I think Max and others are working on other kinds of biases as well.
Mm-hmm.
I'm going to let Arvind say one sentence, and then that's going to finish up this session. If I could ask the next paper, I think it's Elisa is coming up to present, just to get ready, and Fernando has his laptop.
I do think there is something we can extract from all of this that I think all of us vehemently agree on, which is most of what we're saying can be framed as tools for software engineers to test their systems, understand what's going on. And perhaps that is something we can start building right away. Both our techniques and your techniques can be framed in that way. And that can lead to just more data on how these systems are behaving, and that can lead to further conversations and ways to mitigate these problems.
Well, thank you to both sets of authors. Those were fantastic papers. Up next, we have Elisa Celis, who is going to talk to us about how to be fair and diverse. I should mention that the next three papers were contributed papers submitted to this workshop and chosen competitively by our program committee. So I'd like to take a moment and thank our program committee. The first one we've had for this workshop. It's very exciting. And the papers can be found on the conference website, which is fatml.org. With that, I'm going to give you the microphone. And
Okay, thanks. Yeah, it's great to be here, and it's been a wonderful set of talks so far. So thanks to the organizers and everyone for putting this together. So the paper I'll be speaking about today is on how to be fair and diverse. And Amit and Nishith, two of my co-authors, are here. And this is also joint work with Tarun from MSR India. So to be clear, as we were talking about all of these things, there's many different ways that we can think about fairness and diversity, and they can be a bit convoluted sometimes. So just to give you an idea of how I'm thinking about, or how we are thinking about these things, when we think about diversity, what we're thinking about is data that shows differences. So you're looking at different or varied data. So if you're looking at some of these vectors, you can think of vectors pointing in very different directions. And if we have a collection of such data, we think of it as being diverse. When we're talking about fairness, what we're thinking about here is really a protected class or protected attributes, and we want data that is impartial towards these attributes, whether that be gender or race or any of these other things. So on a high level, this is what we're thinking about. And the specific problem that we focus on in our work is a subsampling problem. So you can think of some data set, in this case, images of scientists. And what we want to do is just choose some subset of this data, in this case, a subset of size k. And this is a really basic problem that is quite fundamental to various aspects of machine learning. So very often, we want to do this just as a summarization task, right? If you search, say, on Google Images, Google still needs to choose some subset to present to you. So it can be an end goal, and that is primarily what we focus on today. But the training goal is also very important. So this data, or this subset of data, you would presumably feed into some algorithm that then does something with it down the line. So for both these applications, subsampling is very important, and both fairness and diversity end up being crucial. So in order to discuss what, more formally, how we're going to talk about fairness and diversity, we really take this data set, and we're going to look at it from two very different perspectives. So one perspective on your left-hand side is an attribute space. So in this case, just as an example, we have our images, and perhaps here we can label them as male and female. So this is just an attribute space. On the other hand, we can think of them, as you saw in these previous two talks, we can look at them the way a computer looks at them, as high-dimensional feature vectors. So they're just vectors in some space. Now, looking at it these two ways, we can take our subset, and now the question is, how do we measure the fairness or the diversity of this particular subset? So when if we're looking at the attribute space, a very natural way to do this is to just look at your subset and look at the fraction of that subset that comes from each of your different attributes. And you can take the entropy, which is just a standard measure of how different these are. So if you have an equal proportion of each of these attributes in your subset, that's when entropy is maximized. Okay, so we think of this as a combinatorial measure of diversity or as fairness. And this is a very old notion. It's been used all over the place in the sciences and in other places, ecology and whatnot. Now, if we look at our vector notion, how do we think of diversity that way? Here we think about a geometric concept. So you can look at your vectors, and you can think about the space that these vectors span out. Okay? And you look at the volume of that space. And intuitively, the larger the volume, the more diverse, the more different these vectors are. They're pointing in different directions, effectively. Right? So formally, if you look at the matrix, if you have a subset S, and you look at the matrix where each column is your feature vector, and you take the determinant of that matrix times its transpose, that gives you basically the squared volume of this space. So this is a concept that's very well studied in ML. It appears all over the place because it does give you that sense of how different the points in your data set are. And one of the reasons why it's been so successful in machine learning tasks is that we know that so one of the reasons why it's been so successful in machine learning tasks is that we know that we can actually sample from this type of set, right? So you can choose some subset proportionally to its volume. So if you have some set that's very diverse, spans a lot of volume, the probability that you choose it will be much larger than the probability that you choose some set where everything is very similar. Now, on the other side, it's very easy, if you don't care about this vector space, to just sample points that satisfy whatever constraints you want on these subclasses. We just look at each subclass separately, choose however many points you want from that subclass, and stick them together to find some set. Okay, so these are really our two notions of, or two metrics of fairness and diversity. Now, it might be a little bit more clear that if we have some subset that is fair, right, that is equally distributed among these classes, that doesn't necessarily say anything about the geometric diversity, right? But we could potentially hope that maybe the geometric diversity is capturing some of these attributes and still managing to be fair. So our first question could be basically, does this geometric diversity capture fairness for us already? And just, I mean, looking at a toy example of some of these, it's clear that they're really quite different things, right? The middle row is maybe the more obvious one. We can have something that is very fair, at least with respect to this male-female partition, right? We have 2 female and 2 male scientists, but these images are all very similar looking, right? And when you map them to that vector space, they'll all be also very similar, have very low volume. On the other hand, we can have very highly diverse in terms of the vector space. The top row, there's images that look very different, but in this case, they're all male. And what we really want ideally is this bottom row, where we have that symmetry. We have very different looking images that are also equally distributed across attributes. So here our question is really, can the two coexist? And clearly, they can on some level, but more fundamentally, can we find such subsets? And why do we want to do this? Again, if our end goal is the data summarization, we would want to present, again, on something like search, varied items, very different items that are also unbiased. And if we look at the training application, there we want to subsample data, ideally in order to reduce biases down the line. If we hand our machine learning algorithm some data that has already been unbiased, the hope is that the end result will also be unbiased. And the reason why, especially for this application, you also want the geometric diversity is that this is what really helps your machine learning algorithm be robust. It needs to see many different examples so that it can learn. Okay, so how do we do this? So we already said that if all we care about is the combinatorial or the fairness, that's easy to do. And if all we care about is the geometric side, we know how to do that as well. But how can we combine both so that when we get our sample, it has both properties? So there's 2 ways we can do this. The first or more obvious way is to perhaps look at each of your attributes separately. And within one attribute, you just do your geometric sampling, right? So here I'm just going to choose 2 equally sized subsets according to what's called the DPP. This is your sampling, your geometric sampling process. And that will give you some sample that is guaranteed to be fair, and ideally it's still quite diverse. The other slightly different approach we can take is do our DPP, or geometric sampling, and now all that we're going to do is condition only select subsets that satisfy this equal split among classes. So we're going to choose one thing all at once, but conditioned on satisfying whatever fairness constraint we want. Okay, so these are 2 slightly different ways, approaches that we can take. As we said, the first one, it's just putting the 2 easy things together. So we know that we can do for sure. One could ask about the second version, is it still efficient? Can we still do this effectively? Because now we're adding some additional constraints to the sampling process. So this is not a priori clear, but what we've shown recently is that actually you can do this. You can satisfy these constraints. So this kind of leads back to a point Cynthia made earlier. What is the cost, right, the computational cost of achieving this fairness? And in this case, we can handle it. Okay, so that's good. We know how to sample in these settings. The question is this really doing what we want? Are we really getting some outcome that is reasonably fair and reasonably diverse. So to test this out, we just tried it out on a little toy experiment. And what we did is we collected some images from Google Image Search, and we just searched for scientist female, scientist male, and also artist female and artist male. So this immediately gives us 4 attributes, right? We have these 4 spaces. And then there's kind of standard ways of mapping these images to vectors. Right? So this gives us the data set that we work with. And what we're going to do is measure these 2 fairness and diversity metrics. And we have kind of our usual geometric, what's called a KDPP, our usual geometric sampling process. We have the 2 approaches that I described to you. And in this case, the constraints that we place is that we take equal amounts from each subset. And as a baseline, we also can just take a uniform sample, just to see what that gives us. So if we do this, what we can look at is, again, the fairness and the diversity metrics. And the first thing that I want to point out is that when I set up this data set was inherently fair. I took 200 images from each of my classes, right? So currently, everyone is equally represented. And of course, if we take our 2 approaches, those are by definition fair, because we forced our algorithms to take equal amounts from each class. So that kind of top flat line in terms of fairness are our 2 approaches. Now, one thing that I found quite interesting and very relevant here is that if you look at uniform sampling, okay, maybe that is expected. It's not going to be perfectly fair. There is some noise there, right? You're not going to get perfectly equal distribution. But if you look at this geometric sampling, you're actually doing even worse than uniform. So by trying to sample geometrically, which we had kind of hoped might take into account our fairness, actually it's not. In this case, it's actually doing worse. Generally, we can see that the more samples we get, they are getting better. But still, this is not quite fair. Now, if you look on the diversity side, we were nicely surprised to find that the PDPP is comparable, statistically comparable to the usual geometric sampling process. So we're not really losing out at all here. Okay, so now let's look at the real question, which is what if this underlying data is biased? So here on the x-axis, we took our data set and we subsampled it, so there was a smaller fraction of male versus females. We still kept all the scientists and artists. So it goes from roughly 10% to the equal 50% of male in the data set. And now what you can see is that if you don't take one of our approaches that is correcting for this bias, especially if your underlying data set is biased, you're doing really badly in terms of fairness, right? Which is expected, but really you pay a lot in terms of this metric. It's on the other hand, if you look at the diversity side, now our algorithm starts to pay a little bit, right? When the data is very biased, you can't get as good diversity as your geometric process, but you don't do too bad. And actually part of why we're doing a little bit worse here is because we had such small data sets. So we've also done some experiments. If you have a much bigger data set, the amount you pay is even less because you have a lot more variety. Here the issue really is if only 10% of our data set is male, we have very few male images to choose from. So that's really where this cost is coming here. And one last thing I wanted to point out here, which also was an interesting observation for us, was that our second approach, when we sample once versus when we sample from each side of the partition, that approach ends up being better on both metrics. So it really is important to be able to take everything as a whole, look at the whole data set when doing this sampling. Okay. So overall, what were the take-home messages from this? Even if your data is fair, and this I find really important, even if your data starts out being fair, by doing your diverse subsampling, you may actually be introducing biases into your data set. So this really is an important problem to look at. Secondly, we want to consider the subsamples as a whole. So looking at these type of processes that combine in one subsample both the different attributes and the geometric diversity is really important. Here I just gave one simple example where we have one partition and we want to split things evenly, but there's more and more complex constraints that one can handle, again, at higher and higher computational costs. And the last point, which really is kind of the most important point here, is that this is something that we can do. We can do this efficiently, we can guarantee fairness, and we don't have to pay too much in terms of the loss to diversity. Now, as I said, the subsampling that I showed you here, this is really just one part, and it's an important part. It's often a very useful end goal, but one thing that we're really interested in that several people have alluded to in the past two talks is what happens down the line, right? This is really the first step. So we have our data set, we take our subsample, what if we feed it into the algorithm? So the nice thing about this approach is that right now we don't have to dig into the algorithm, right? It's kind of a pre-processing step. We hand an unbiased or a debiased subsample to the algorithm, and now what we would really want to see is what end output do we get in terms of bias, in terms of accuracy, and whatnot. So that is really the main direction I see here for future work. And that's it. Thanks. Questions? Sorry, questions now or later?
We'll go ahead and take questions now. If you have a question, please do come up to the center aisle and use the microphone.
Sure.
Okay. Thank you for your presentation. I would like to have your opinion, in fact, with regards to fairness definition. For sometimes collective fairness can be against individual fairness, and even the concept of fairness seems to be subjective somehow, and depending on the context and the use case. So what's your opinion? Should we have I mean, I don't believe that there is a unique definition of fairness.
Yes, thanks. I completely agree. So part of the issue here is how do you decide what is fair and what is not, right? And a lot of this has to do with the end, I would say in this kind of future work part, with the end application. Here our notion of fairness was really fairness in the data set in the sense that all classes are represented, and all classes are represented well, right? Sorry?
Should be stated to say it's fair with regards to what?
Yeah, fair, yes, absolutely. So fair with regards to what, and here what we're considering fair is equal representation in the data set. So we're not saying anything necessarily about the outcome, but we're saying that all classes are being represented and represented diversely in the data set. Absolutely. Anything else? Thank you.
Well, thank you, everyone. If there are no other questions, I'd like to invite Fernando Diaz up to talk to us about, let's read it's a long title. Fernando will tell us. It's exploring or exploiting social and ethical implications of autonomous experimentation in AI, with a large number of authors as well.
Do you guys know there's lines on the ceiling? I've never seen that before. All right, so thank you very much. This is joint work with Solon Barakis, Sarah Bird, Hannah Wallach, Kate Crawford, and it's all conducted at Microsoft Research here in New York City. So just to be clear, we're all coming from pretty diverse backgrounds, but that seems to be representative of the FATML community, so that's great. So several of the early presentations have focused on measurement and the measurement of fairness and the optimization of so-called fairness-aware algorithms. This work that I'm going to be presenting today will focus on experimentation in online services such as web search engines or news sites. More precisely, this work deals with autonomous or algorithmic experimentation and the ethical questions that this practice might raise. So I'd like to begin by putting this work in some context. So first, I want to be kind of specific about the domain. As with previous presentations, the slide's supposed to be black, so don't worry. As with previous presentations, we'll be considering the situation where machine learning is making decisions about individuals. So for example, hire or no hire, or add 1 versus add 2, based upon information collected about that individual. So for example, SAT scores or state demographics. As a running example, we're going to be using navigation. So let's say I want to go from NYU to Columbia. The job of the system then is to provide me with some satisfying route between the two. Similarly, if I want to go from Broadway Junction to Broadway Theater, I might be provided this route. Now for simplicity, I'm going to assume that the system's actually recommending a fixed route as opposed to dynamically adjusting that route in transit. Now, I'd like to provide some additional context from the perspective of supervised learning. So we might have some data set of routes gathered by, say, GPS data from taxis or cell phones. Now, if these training routes are gathered so that some areas in the city are over or underrepresented in some systemic way, we could imagine a machine underperforming for underrepresented parts of the city. So for example, if our training data comes primarily from Manhattan, the machine might be less confident about effective routes within Queens. Alternatively, if the route selection reflects some unsubstantiated bias in the driver to provide the training data, the machine may inherit the bias from those drivers. So for example, if all of the training routes avoid certain neighborhoods with certain demographics, the machine might also learn to avoid these neighborhoods, perhaps degrading the effectiveness for drivers from those areas. Now, dealing with the bias in supervised learning has been addressed in a lot of previous iterations of FATML, as well as previous talks today. And we're going to return to this in a few minutes. Before that, I'd like to discuss online experimentation. So for those of you unfamiliar with the topic, I'm going to provide a pretty quick summary. So most online services today, such as web search engines or news sites, conduct what's called A/B testing in order to optimize system performance. So for example, if a website is trying to decide between a 2-column layout and a 3-column layout, it might present 50% of its users with a 2-column layout and 50% with a 3-column layout. After some period of time, the engineers will inspect the log user data and see which layout actually improved the user or revenue metrics. Many of these experiments might be considered relatively benign, especially interface experiments. However, let's return to our routing example. So let's say engineers are interested in seeing if users respond well to more scenic oceanside routes compared to shorter or quicker direct routes. So what they're going to do is provide 50% of the users with the quicker, less scenic route and 50% of the users with the longer oceanside routes. Let's say I want to get from Brooklyn Heights to JFK in order to make a flight. The quicker route might be taking Atlantic Avenue and arriving at JFK in a half hour, optimistically. However, if I'm lucky enough to be in the scenic experiment, I might be sent down through the Belt Parkway, arriving at the airport in an hour, potentially missing my flight. Now, this type of experiment has raised concerns from both the popular press as well as the academic community in response mostly to the emotional contagion experiment from a few years ago. Now, notwithstanding these issues, experimentation provides the opportunity to address some of these issues with biased training data. For example, if we're able to, at fine granularity, make experimentation decisions, we could get a more representative sample of the data or one that avoids systemic bias. Take predictive policing as an example. Let's say we're trying to decide where to dispatch police to a neighborhood based upon features of that neighborhood, perhaps including demographic information. If the model's trained on a sample overrepresenting certain neighborhoods as high crime areas, policing decisions may reinforce these observations, as we saw earlier. Now, if the system randomly decides to send police to areas predicted to be low crime and observe high crime, it can incorporate this information and adapt the model, thus recovering from the biased training data. Now, this is precisely the strategy of a family of algorithms which balance exploiting and exploring. These algorithms have been used primarily for domains like news recommendation and web search, where a machine needs to determine which article or which ranking to present to different users. So for example, here, if I have a population of red, green, and blue users, the system, in order to determine the appropriate article for the blue user, might initially be uncertain and therefore present random articles until the user provides positive feedback. So here, presenting the red article, receiving negative feedback, the purple article, again, negative feedback, and finally, when it presents the blue article, it gets positive feedback. So this behavior is referred to as exploration and is often guided by uncertainty about what the optimal action might be. So after enough exploration, the system might determine that the optimal thing to present to the blue users is, say, the blue article and receive positive feedback. Now, nevertheless, in a real system, uncertainty can arise throughout the lifetime of the process, depending on how unusual a particular user or a particular context might be. Okay, so let's say we have this population of users where blue is very well represented, followed by red, and then green is a minority. In an explore-exploit system, we might observe improve performance over time at a rate that might be proportional to the size of the group. It's this behavior that allows the explore-exploit algorithm to potentially recover from some of the biased training data that you would observe in supervised learning systems. Now, compared to A/B testing, autonomous experimentation is conducted on a much more granular scale, making these decisions oftentimes on a per-user basis as opposed to per cohort. As a result, the family of techniques has often been described as A/B testing on steroids. Now, given this connection to A/B testing, we felt that it was important to revisit some of the questions raised by the online experimentation in general, say from the emotional contagion experiment, and whether they would be exacerbated in autonomous experimentation. The cost of the users enlisted in exploration for us is clearly compensated for by the increases overall utility provided by these discoveries, as suggested by the superior long-term performance of explore-exploit algorithms. Therefore, exploration seems exceedingly well justified if we're to evaluate it on utilitarian grounds. However, exploration may nonetheless raise a number of serious concerns well recognized in other ethical traditions, say from research ethics. So we're going to suggest analyzing these algorithms using research ethics principles, particularly published by the Belmont Report in 1979. This report established 3 basic ethical principles: respect for persons, beneficence, and justice. Respect for persons protects human autonomy, allows for informed consent, and requires researchers to be truthful to those participants. Beneficence embodies the idea of do no harm, with the aim of minimizing any risks to the research subjects while maximizing the research benefits. And finally, justice addresses the process of distributing risks and benefits to potential research subjects in a manner that is fair. Now, in the remainder of the presentation, we're going to argue that autonomous experimentation systems challenge these 3 basic principles. So, autonomous experimentation systems conduct exploration by taking potentially suboptimal actions in order to discover the relationship between these actions and their outcomes. By subjecting users to potentially suboptimal actions, some users will experience inconveniences or risks not experienced by other users. For example, a system may want to confirm that a previously slow route is still slow by deliberately sending some users along the slower route. Such decisions expose the users to risk, even though the goal is to improve system performance as a whole. Now, it's this disparity that raises the question about who should act as an explorer and who should actually exploit the information that we're discovering as a result of our exploration. One obvious answer is to require the explorers to be selected uniformly at random. Unfortunately, even though the selection procedure is technically unbiased, it can still violate this ethical principle of autonomy. Now, we're going to argue that in absence of informed consent, Such experiments take advantage of users' ignorance and potentially direct them to engage in activities that depart from their goals, preferences, and expectations. A person who will miss their flight or be late to the airport might decline an invitation to serve as an explorer if there's another route that might provide them ability to access the airport early. Now, respect for persons dictates that the importance of allowing users to make such decisions for themselves in an informed manner is important. Even if exploration improves the system performance as a whole, it may not justify risks to any specific user when we're considering autonomy. Now, in many cases, when we're certain about the optimal action, say the right news article to present, we probably do not need to explore anymore. As a result, many algorithms explore at a rate that's proportional to the uncertainty about the optimal decision. Because uncertainty arises from the lack of information, users who belong to some minority group about which there's proportionally less information by definition may be more likely to serve as an explorer. In our previous example, the smaller green population will incur a larger per user exploration rate than the blue population. In other words, autonomous experimentation systems can disproportionately target users who do not resemble the majority class, in some cases because they belong to some historically disadvantaged group. Now, this raises questions that relate to justice. In other words, the process of distributing risks and benefits in a manner that is fair. Unfortunately, the standard notion of justice does not translate cleanly to autonomous experimentation. In a traditional human subjects experiment, upholding justice means ensuring that one group does not bear most of the risks while another accrues most of the benefits. However, in autonomous experimentation systems, disproportionately experiment on minority users, these same users are the ones that stand to benefit from precisely those experiments. As a result, a more pertinent question is whether the extent or nature of the experiment is actually necessary. Would other experiments with fewer risks be equally effective at benefiting those minority users? This is exactly what beneficence tries to capture. Here, the goal is to try to ensure that any risks to research subjects are minimized while maximizing the research benefit. Indeed, upholding beneficence sometimes requires researchers to consider using alternative research methods, which we may have to do here for minority populations. Now, in a traditional human subjects experiment, informed consent means that the potential research subjects must be provided with information about the experiment and given the opportunity to agree. Unfortunately, it is much harder to obtain informed consent from users of an autonomous experimentation system. First, the reasons for actually performing the experiment depend on the internals of the system. Its current representation of the environment, its set of possible actions, its strategy for selecting explorers and actions, and its assessment of potential risks and benefits. The transparencies about the reasons behind experimentation in a manner that's unambiguous and that accords with the user's notions of risks and benefits is not easy. Second, the number and range of experiments and the speed at which they are typically performed may make enacting informed consent extremely difficult. Imagine trying to get informed consent for every web page you browse. Now, these obstacles to obtaining informed consent also make it difficult to develop procedures for ensuring accountability. For government-funded human subjects research, the common rule requires that institutional review boards review all experiments and evaluate research protocols and methods and assess the potential risks and benefits. There's no clear analog for autonomous experimentation systems here. One possibility is that is an automated checks and balances mechanism, perhaps as a part of the system's reward function for monitoring the system's actions and to penalize experiments that an IRB would find problematic, for example. In many scenarios, although it is likely that such a mechanism would be, such a mechanism would be accomplished by some form of human review. This hybrid approach would make it possible to share accountability between the system designers, the people designing the agent or the system, and external reviewers who are evaluating or judging the experiment decisions conducted. But then again, this raises a challenge of actually communicating the reasons for performing an autonomous experiment to the human decision makers. In addition, it would slow the system down and obfuscate who users should hold accountable if something should go wrong. Finally, regardless of the procedure for ensuring accountability, the task of assessing potential risks and benefits to users is non-trivial. In autonomous experimentation systems, risks and benefits are typically derived from some behavioral data such as clicks or wearable sensors, often by some other machine learning system, or which may be crude or even vulnerable to errors or biased training in itself. If a system's assessments of risks and benefits are inaccurate, then any decisions based upon those assessments will necessarily also be inaccurate. And so we're stuck. So in closing, we're at the beginning of a new phase of experimentation with autonomous experimentation systems increasingly found in critical infrastructure such as transportation and healthcare, and everyday infrastructure such as search engines. However, despite the ongoing debate about existing research ethics regulations and their applicability to data science, researchers have largely ignored the unique risks posed by autonomous experimentation. As we have shown in the presentation, autonomous experimentation challenges the ethical principles codified in the Common Rule, respect for persons, beneficence, and justice. Therefore, we believe that more research is urgently needed in order to fully understand the social and ethical consequences of autonomous experimentation systems. Thanks.
Thank you, Fernando. We have about 3 minutes for questions if people want to come up to the center and ask questions. And yeah.
Hi, it was a great paper. You picked the right ethical items to think about, but I wonder if the distinction in the traditional biomedical area between the operation or practice of medicine and an experiment is relevant here. How do you distinguish the normal operation of a navigation system versus, an experiment that's being conducted in that context?
Well, I mean, experimentation is sort of built into these systems these days. I mean, systems that do explore, exploit, for example, it's all part of the practice. So essentially, depending on the algorithm, everything might be an experiment. Yeah.
So it's interesting to compare this talk to the talk earlier today by Jamie Morgenstern on explore, exploit for solving fairness, where she showed theoretically that we need to have explore, exploit in order to achieve fairness in learning. And here we're seeing that if we do explore, exploit, then we are inherently not fair.
Well, that's not, I mean,
basically,
I'm seeing something slightly different. I think that paper and the paper that's going to be presented immediately after me is going to address some aspects of what I'm raising here. But it doesn't address things such as respect for persons or even beneficence.
Okay, so just real quickly, is there a way that you can think of to maintain the theoretical guarantees that we see in, say, the Morgenstern paper while achieving some of these additional goals that you're putting forward?
I mean, this is a recurring question at SafeAtML where we ask, like, can we guarantee fairness and at the same time provide some of the guarantees about accuracy and whatnot? Sure. I mean, the point of this paper was mainly to raise a new set of ethical principles that we may want to incorporate into these algorithms. Okay.
Thank you, Fernando. Our next paper is Rawlsian Fairness for Machine Learning, which I believe is being presented by Michael Kearns. You're Seth Neal. Okay. Thank you, Seth.
Yeah. Okay, so I'm very honored to be speaking on behalf of our research group, which does include Michael Kearns, as well as Matt Joseph, Jamie, who you've already seen, and Aaron Roth as well. So we've seen a lot of discussion today about how, given a black box machine learning algorithm like, say, Word2Vec, how you can sort of analyze the discriminatory behavior and how you can perhaps post-process it to try and achieve more fairness. And then we've seen a presentation following it which suggests maybe instead of altering perception or how the algorithm is receiving the data, we should alter action. And this talk is sort of in that direction, which says, let us propose sort of a general fairness definition, which we term Rawlsian fairness, and then from the ground up at every stage of the learning process, let us try and be fair with respect to that definition. So I'm going to briefly situate our definition of fairness, Rawlsian fairness, which is the same definition Jamie used earlier, in the context of other fairness definitions that have been proposed. Then I'm going to walk everyone through an example of how you can apply Rawlsian fairness in a sequential decision-making framework, and sort of analyze some interesting theoretical and empirical guarantees that we can show for our algorithm. Okay. Yeah, so again, this is our research group all at Penn. I think we've already covered that. Okay, so the first definition I want to highlight is from the Fairness Through Awareness paper from 2011, which says that any two individuals who are similar should be treated or classified similarly by an algorithm, and that's what it means to be fair, that a fair algorithm treats similar individuals similarly. And that does presuppose that we already have a notion of what it means for two individuals to be similar, or a distance metric. So our definition will sort of also say that it's fair to treat similar individuals similarly, but we'll also propose a specific kind of general notion of what it means for individuals to be similar with respect to a particular task. And another definition, which we've also seen in one of the 5-minute talks today, is that given some sensitive information like race or gender, a fair algorithm should not ignore them completely, in that the prediction shouldn't be independent of the protected attributes, but conditional on the outcome. They shouldn't depend on the sensitive information. So it's this, among people who are classified a certain way, or who should be classified a certain way, their true quality is the same. Their predictions should not depend heavily on these sensitive attributes. And our definition also captures part of that, although it's a little, it's not immediately obvious. And the last thing I'll highlight again is that we're not taking some batch learning model or some model that's already been made and trying to give fairness guarantees for it or prove properties of its fairness. We're starting from no information, and at every step of this sequential learning process, we're going to try and enforce this fairness definition. And so we're simultaneously going to be trying to be fair at every step, but also to learn and improve our model. Okay, so a brief philosophical motivation for our definition. We call it Rawlsian fairness after the philosopher John Rawls. I'm not well versed in Rawlsian philosophy, but essentially we're trying to encapsulate this notion of fair equality of opportunity, which says that two individuals who are of the same talent, natural talent or ability, should have the same prospects of success in the system. And so what that means concretely in our setting is that two individuals who have the same value with respect to the classification, so the same probability of paying back the loan, for example, should have the same probability of receiving that loan. And so that's what throughout this talk, that's going to be our working definition of fairness. So before I briefly introduce the learning model that we're studying here, called the Contextual Bandit Framework, I want to mention that this definition and sort of the ethos behind the Rawlsian fairness definition applies to a wide variety of machine learning frameworks, which is why two of the other papers today are also using this exact kind of Rawlsian fairness, except in reinforcement learning, and one studies a similar bandit problem. All right, so the contextual bandit in a simple way is as follows. Say we have an unnamed bank, and at every time, individuals from 3 different racial groups are arriving. They can't sue me because they don't exist anymore. So at every step, we view an individual's credit history represented by the shaded papers at the right, and other relevant characteristics about them, and we make a decision whether or not to give them a loan. And suppose for the purposes of this talk, we're only giving one loan at every time. So at the beginning, we have no idea how this credit information and these characteristics actually maps to the quality of the individual, how it actually maps to the likelihood they'll pay back the loan or how much money they're going to pay back on the loan. So simultaneously, while assigning these loans, we're going to observe who pays it back. And then at each step, after we observe how much they pay back, we'll update our sort of idea about the model, and we'll hopefully make better predictions over time. Actually, we'll prove that we will. now we're going to define what it means to be Rawlsian fair in this sequential framework. So we require that at every time t over all t greater than or equal to 0, if an individual I, so an individual from one group, one racial group, for example, gets a loan with a higher probability, so the probability that it's chosen as the guy at that time who gets the loan is higher than an individual J's probability of getting the loan at that time, then that individual must have a higher quality, or it must have a higher repayment than the loan it was favored over. So that's sort of exactly modeling this idea that if an individual has more natural ability or more true quality, it should have a higher prospect of success in our system, and that's the only way that can occur. So for the purposes of analyzing, proving things theoretically about the algorithm, we assume that the mapping from the information about every person to the true quality is a linear function of the observed features. But again, that's not an artifact of the fairness definition. That's for the purposes of the analysis. And it's obviously a very commonly used model. So just to quickly summarize the model before we get into any analysis, at every time t, we're going to have individuals from these, say 3, but k groups arrive, each with a vector of features, some relevant information. Then one of those people is going to be chosen to get a loan, and then we're going to observe the amount of money they pay back as a linear function, an unknown linear function of that person's features, and then we're going to update our information about these linear functions, and then we're going to repeat the process. And there's noise here as well. Okay, so yeah, this is the formal definition, which just, again, is exactly what I said. The probability of choosing an arm I is greater than the probability of choosing an arm J, only if the true quality of I is higher than the true quality of J. And we specify that this happens simultaneously over all t greater than 0 with high probability. And there's something a little subtle there. You could imagine a weaker definition of fairness which says, at every round with 99% probability, we're going to be fair with respect to this definition. So at every round, there's a 1% chance that we're being unfair. We're saying that over all of the runs at all t, the entire span of the algorithm, we're going to be fair at every single round with probability 1 minus delta. And the reason we do this is because if you just require it on a round-by-round basis, that would allow for discrimination against, arbitrary discrimination against individuals who occur very rarely in the data. So if our delta was 0.01, if less than delta fraction of the time an extremely qualified individual from a certain ethnic group came along, if we had this weaker definition, then we would simply be able to never give them a loan, and that would be fair. But this definition prevents that. Okay, I'm not going to dwell here too long, but regret is essentially the standard way of measuring the performance of an algorithm in this online setting. And it says, what's the difference between how our algorithm actually did, or the expected difference, and what is the best you could possibly do if you truly knew the linear function. So the best possible algorithm would always play the individual with the highest quality, which, by the way, would be fair with respect to our definition. But obviously, you don't know those true linear functions, and so you can't always do that. And so this quantifying how this regret performs of our fair algorithm is a way of saying, what is the cost of fairness? How does our regret of our fair algorithm, which I'm about to define, compare to the regret of the unfair algorithm, the best algorithm that we can do? Okay, so the main theoretical result of the paper, and again, there's not too much time to get into it, is that we prove this regret bound for a fair algorithm by our definition. And combining that with previously known lower bounds and from the literature, we know that we can precisely kind of quantify the cost of fairness in this case. So without requiring a fairness constraint, if the best you can do is something like O tilde of root TD, and we're showing an upper bound of D root TK cubed, then we can sort of say that the cost of fairness is at most root dk cubed. So that's a nice way of sort of formally quantifying the trade-off that's been discussed all day about accuracy versus fairness. Okay, so I'm going to briefly talk you guys through the high-level idea of how we form this FAIR algorithm. So at every time t, we're going to form a confidence interval around the payoff of the mean from each arm. And it's just a linear function, so that's something we know how to do in many different ways from statistics. And then we'll have those confidence intervals, and you'll see on the next slide, we'll chain them together, and we'll form a chain of confidence intervals that are all connected to the best arm at that given time. So some of the arms will be in that chain, and others won't. And then finally, we'll just pick an arm, pick a person to receive a loan uniformly from the set of arms that are chained to the best guy. So how that looks is as follows. So we have a confidence interval for the top arm, the second best, the third, the fourth. And as you can see, the second confidence interval intersects with the top confidence interval, which means that there is some chance that that arm that we think is the second best actually has a higher mean because their confidence intervals intersect. So to comply with our definition, we have to play them with the same probability. But then that reasoning means we have to play the third arm with the same probability as the second arm, since those confidence intervals overlap, and the fourth arm with the same probability as the third arm. So by the transitive property, our fairness definition requires we have to play all of those arms with the same probability. But those bottom arms don't intersect any of that higher group, and so we don't play them at all at this step. And one thing that's worth noting is that the optimal algorithm that doesn't worry about fairness just plays the top arm, the arm with the highest upper confidence bound, UCB. So this is sort of a nice conceptual kind of transition from that optimal algorithm to a fair algorithm. Okay, so quickly, this shows how the chaining takes place. I guess one key thing to note here is that in the bottom slide, you can see the gray band measures the width of that big chained confidence interval. So all the widths of those confidence intervals that are played from uniformly random at each step. And over time, because we're learning more and more about the linear parameters that govern those arms, the width is shrinking. And that's sort of a visual proof of the fact that our algorithm actually is playing with no regret asymptotically. So we're eventually converging to playing the best arm. And that's a key property. So there is this cost of fairness, but it's not so high that you can never actually perform the task. Okay, so before I finish up, I'm going to highlight two sort of empirical findings from the paper. The first one, there's a couple of different in these plots, but I'm just going to focus on the middle one, shows how the trade-off of the difference between our algorithm and the best algorithm, so the difference in average regret between those algorithms, varies as a function of the number of arms that we have, the number of people arriving to get loans at every time. And as you can see, let's focus, I thought I might have like a pointer here, but let's focus on the green line in the middle of the middle plot. So as you can see, as k starts to vary with very low values of k, the difference in regret is very low. So our chaining algorithm is doing almost as best as the best algorithm that we can do. But there's almost like a phase transition around k equals 8. And then all of a sudden, as k is increasing up till about 35, there's a lot more, the difference in regret is increasing. And that's because K has hit the point where there's a lot of chaining occurring. And so we're not actually playing that top arm. We're being forced by our fairness definition to play a lot of suboptimal arms that are in the chain. And then that starts to level off around 40 because now there's so much chaining going on that we're basically playing randomly among all the arms. And so the regret is the difference is going to be constant there. And then we have similar plots varying T and D. But that information's in the paper. So I think more interestingly, we also define a notion of structural unfairness. And without getting too much into it, we say that the structural unfairness with respect to an individual, so this is an element of, I guess, the action space. So what that really means is an individual as represented by that vector of features. We define the structural unfairness to be the the probability that that individual is discriminated against by an algorithm, given that it's involved in a round where an unfair decision is made. So if it's involved in a round where an unfair decision is made, then it could either be benefited by the algorithm or discriminated against. And discriminated against being like it has the top quality but isn't chosen, and benefited being it's actually suboptimal but the algorithm gives it a loan anyways. And so we construct a basic instance where we sort of plot the structural unfairness for every point that could possibly arrive. And this is an example of, so we're in D equals 2, so there's 2 features, and then we're plotting the structural unfairness for all these points, and this is what our fair algorithm produces. So the key thing to note here is that at every value of x, every cross-section, the color doesn't change, and the color is indicative of the height, the amount of discrimination. And that's because in this example that we set up, the true quality is just a function of x. So that's what you'd want to see. Individuals who have the same true quality have the same chance of being discriminated against. So that's why the curve has this nice property that every sort of x cross-section has the same height. Now we took the same exact data generating process, and we ran the standard best practice UCB algorithm on it. And as you can see, along a specific cross-section of the data, which is a subset that we had designed carefully using sort of like a heuristic about why these algorithms could discriminate, there's actually like a massive spike in the probability that it's victimized by the standard algorithm, even though the true quality of those points on the diagonal are exactly the same. And so this is just a kind of a compelling visual representation of the exact problem that can happen if you just sort of blindly don't incorporate a fair algorithm. So I guess to summarize, the contributions of this paper are we propose a flexible definition of fairness that extends to a lot of other frameworks. We derive a sensible algorithm that complies with our definition, and there's the more mathy parts of the paper. We prove a sort of technical regret bound on the fair algorithm to precisely quantify the cost of fairness. And then through these empirical experiments, we demonstrate why in this online learning setting, it's very important to try and incorporate notions of fairness. So that's it. Thanks.
So since we're a little behind, I think we have time just for only one question. Seth, I'll let you pick someone. And in the interest of saving time, if you could just shout out your question, then I'll repeat it for the live stream.
I really like this definition. I just don't understand in this setting what the good regret bounds are. So it would be Rawlsian fair to just like reduce to offline learning. So just set theta equal to 0, randomly sample, pick the best theta based on the data that I got, and then just play that. So how, like, quantitatively, that seems like really naive and dumb. So quantitatively, do you know the improvement over that?
Right, so what you just said is that you're saying randomly sample for a given prefix of steps.
Which
right,
if you have exponential...
But over those rounds, you're incurring a lot of regret. So that would be one way that you could do this. And I think the dependence on t you'd get from that is like t to the 2/3 or something. It's not as good as the algorithm that we propose.
Well, the idea being... Oh, if you set theta equal to 0 for some fixed period of time initially, it's not Rawlsian fair?
So the important thing that you're not doing is taking into account the confidence intervals. So your empirical estimate is what theta is. It's not something you get to set. It's not certain. It's always some uncertainty. And if you don't take that into account, it's not going to satisfy.
Okay, so that you actually can't play that out.
The algorithm you described would not satisfy this.
Okay, yeah, I guess I thought what you were suggesting is randomly sample for a prefix of rounds, which would be Rawlsian fair, and then sort of apply this similar strategy.
That is what I was suggesting.
Okay, but maybe we can talk offline about that.
All right, well, thank you, Seth, and let's thank everyone who spoke in this session. And then for one more very brief bit before lunch, I'm sure everyone is very hungry. I'm going to hand it over to Solon.
Hi, everyone. Thanks for bearing with us, and I know we're running a few minutes late. I just wanted to take this important opportunity first to recognize a number of folks in the room who actually come from federal regulatory agencies. We have representatives here from the Federal Trade Commission. Is that person here? Want to stand up and identify yourself just quickly? I do this actually with a purpose, which is that I would hope that the people in this room who are interested in seeing their work translated into practice actually approach these people and talk to them about how some of the work they're doing can be relevant to government practice. So if you're interested, anyway.
I'm Jeff Pellegrino. I'm the research director in the FTC's Office of Technology Research and Investigation.
We also have people here from the Consumer Financial Protection Bureau. Anyone in the room want to identify themselves?
I'm Bryce Stevens. I'm an economist in Section 2 from the Office of Research, and I work with a team of folks who do analysis of real fairly. I'm Aaron Schroeder, and I'm everything but the section sheet part of this. Alan's here too, Alex. And I'm Albert Shang, I'm an economist, counsel in the Office of Fair.
Great, and we also have some folks from the Equal Employment Opportunity Commission. And finally, I think we have someone from Treasury. Is that right?
My name is Austin Hinkle. I'm the Senior Policy Advisor from Treasury, Equal, and
So we're going to break for lunch in a moment, and I hope people will come and introduce themselves to the folks who just introduced themselves to you. But before we do, I have the great privilege of actually being able to introduce you all to the chair and commissioner of the New York City Commission on Human Rights. I am going to terribly mispronounce your name, which is going to be terribly embarrassing because my name is always mispronounced. Carmelyn Morales, who will speak to us today about the agency and some of the work that they're thinking of doing on these topics.
I will be quick. Far be it for me to keep anyone from lunch. And first of all, I wanted to say, one, how kind of surprising it is for me and how kind of gratifying it was for me to walk into a room and see so many people here interested in this topic. For the perspective of government, as some of these other government folks could probably tell you, and from the perspective of somebody who is looking at a lot of these kind of big data issues from a discrimination and kind of fairness framework, it's really exciting to see that so many of the people who are really kind of the first line defenders of fairness and transparency and accountability are so interested in this subject matter and on taking on this work. I also just want to take a moment and say, I almost want to take a picture of myself here because, while my mother was chasing after me when I was a kid to, practice piano, my dad was like chasing after me while I was in elementary school to learn Fortran. And if he knew that I was in this room and not like surrounded by books with lawyers, he would be ecstatic. So thank you for giving me that opportunity to share with my parents. So I am the chair and commissioner of the New York City Commission on Human Rights. We are the city agency that is charged with enforcing the city's very broad anti-discrimination and anti-harassment protections. So there's part of our agency that does kind of civil law enforcement work. Kind of the three main areas we do that in are in housing, employment, public accommodations, and we have some other areas, but those are really kind of the big areas that we work in. We take complaints in from the public. We also, on behalf of the city, when we know that, or when folks from universities or from elected officials or other kind of community-based organizations, when they identify issues in those areas where they think that there is, a pattern and practice of discrimination, or there are actions that we should be addressing, they'll also contact us. And without having somebody come forward and saying, hey, I've been harmed by this, we as the government have the ability to affirmatively investigate those issues and sometimes also affirmatively litigate those issues. So it's a very important part of the agency. The other part of our agency deals with kind of going into different communities or working with different constituent groups and educating them on the human rights law. So educating them on, what their rights are, what they have a right to be free from in terms of discrimination and harassment, and frankly also what their obligations are. How can they prevent discrimination or harassment from occurring in their housing units, in their businesses, as employers? And to me, certainly, as technology is increasingly becoming the area where I think people are getting their news, they're getting their information, that is, technology is kind of the big influencer in the room. We are seeing a lot more ways that people can use technology, of course, to intentionally sometimes and sometimes unintentionally treat people differently, in all those different categories. So again, it's really wonderful to see so many folks out here. As we've been working with different groups on, educating them on rights as well as obligations, what's been really important for us is really figuring out how we can have impact in certain areas. Sometimes our impact is on enforcing the law through, initiating these investigations and then litigating these cases. But quite often, and mostly, as in the last almost 2 years that I've been at the commission, a lot of the way that we actually impact change is impacting behavior. Making people aware of how their actions, their decision making influences outcome, making folks aware of how they're focusing on something that may be because of what has been put out into the general public, maybe because of the information or the misinformation that has been put out there. Maybe that's influencing a way that people think about a certain issue, but correcting the record so people actually understand and actually realize that sometimes that information is wrong. One of the ways I think that really kind of connects to some of the work that you all do is, one of the first big city campaigns that we had launched when I came in as the chair of the agency was a citywide campaign on credit history discrimination in employment. And it had been this area where for however many years long, employers were very used to either on their own or contracting third parties to kind of cull together folks' credit history information through all the various things that are available in public records, through other kind of credit history related information. They'd put together these reports, they'd get this like one score, and based on that one score alone, kind of regardless of what a person's qualifications were for a job, or regardless of how maybe past employers had rated that person's performance, that person would be kind of put on the reject pile for certain things. All of this while knowing that, or while not knowing actually for a lot of folks, while not knowing that there was actually no research connecting any sort of credit history to trustworthiness for applicants for employment. And so this administration worked with the city council. We worked with other organizations that saw how credit history was being used in this discriminatory way in order to disadvantage well-qualified applicants, particularly applicants who were in communities of color, particularly applicants who were women, and that is because still it's the case that disproportionately women tend to be the kind of caretakers or caregivers in family units, and so are less likely to be able to build a solid credit history. It disproportionately influenced folks who had gone through divorces, who had been in school and had past payments with some of their student loan debt, things of that nature. So kind of very similarly here, we find ourselves now also kind of tackling this question of how we can work with people who are in the field of and studying and figuring out and really kind of designing the different techniques for machine learning to make sure that as you are designing these different algorithms, you're thoughtful of the different ways that the information could be used. We, as an agency, from our enforcement perspective, we're already seeing how some of this is already coming up in employment. And our kind of sister agency on the federal level is the EEOC. It's great to see somebody here from the EEOC. I actually just came from a conference when I was talking with the chair of the EEOC, and we were talking about already in the area of employment, the focus that has been put on this issue. But I also want to make sure that we're also focusing on some of the other areas like housing and public accommodations, because that increasingly in our agency is where we are seeing these things kind of creep up. And in housing, for instance, we're seeing the ways in which, whether you're looking at real estate agents or you're looking at big housing providers and big companies are contracting out to third parties and the third parties are providing them or purporting to provide them information that helps them kind of wean out people who speak second languages, people who they think would be coming from immigrant families, people who would be have different names associated with them. So of course that would have a lot of different hits in our anti-discrimination laws, right? There's different ways that could be used to discriminate against folks because of their immigration status, their national origin, their race, their gender identity and gender expression. If they're transgender, they're likely to have some changes in their names. So there's different ways that this could be used, and of course, if they're kind of selling themselves in this way, there is the intention of discriminating in that area, and where there's the intention of discriminating in that area, then certainly under the city human rights law, even if they are a third-party company who is raising these issues, even if they're not the actual housing provider, there is the possibility of also prosecuting actions under the city human rights law against those folks. Again, what we're finding, I think more than the intentional discriminators, though, are the folks who aren't really thinking of it from that way. They're not thinking of the ways that information that's being culled or kind of the data that's being fed into the algorithmic data plans, that they're being kind of colored, right, by kind of the human touch of those things. And so again, it's really important that the folks who are, on the front lines of doing that, on the front lines of putting together conferences like this, are having these discussions and putting that out there. So you see how your information is being used, you see how your work product, frankly, is being used, and you have ways of, like the Rawlsian fairness of trying to preclude that from occurring. I think also, outside in the general public, people tend to think, it used to be the case that people used to think, well, if it's in a book, if it's in writing, well, it must be true, right? And I think that very much in the public, people think too, well, if it is produced through, through machine learning, then it must be completely unbiased. It must be completely objective. And I think certainly that is oftentimes the objective. But people also don't realize how much information is actually influenced by the people kind of feeding in the information. And I think that's always something that we have to be critical of. It's great that we're able to work, I'm told that 70% of the room right now is technologists. There's about 30% of the folks who are here who are kind of policy and law related. I think that increasingly we're going to see a lot more, of these types of gatherings, and you're going to see a lot more of the lawyers and policymakers really interested in working with all of you and getting your ideas of the ways that we can be thinking through things, not just from the enforcement realm, but also through the impact realm. The City Commission is very interested in this issue, and so if there are folks wondering, especially right now in this day and age, we've been getting a lot of inquiries in the last week, if you could imagine, of people saying, hey, what can we do to be working on human rights? What can we be doing to be making sure that our communities are not discriminated against? There's a lot you can do, and certainly in this area is extremely fertile ground. So if people are interested, please do come and see me afterwards. I have 2 other folks here from the Commission on Human Rights. And also you can contact us through our website, which is nyc.gov/human rights. So thanks again, and thank you for doing all this important work.